everybody. Here we are to wrap up Chapter 2, Section 4, Systems and How They Respond to Change. Last part of Chapter 2, and this one should be pretty short, as basically a fireside chat today, if you will. Not a lot in the way of demos, so here we go. All right, first off, just what is a system? A system can be anything, a set of components that interact in a regular way. The human body is a system. You know, we eat food, we grow, we develop, we use energy, produce waste. A forest can be a system. Energy comes into it, typically in the form of sunlight. It produces oxygen, it uses carbon dioxide, creates waste, gives off heat. Television system is a system. You plug it in, takes the energy, does certain things, and produces certain things. Now, all systems have certain things in common, if you will. They're going to have inputs. Things have to go into the system. Like with your television, electricity goes into it, into the forest, the sunlight comes into it. In my human body, I put food into the system. They're going to have certain flows. How the forest, as everything comes into the forest, it flows through it. Energy comes in, it goes into the chlorophyll, gets processed, etc. Certain flows, the electricity goes in, the images and the sound flow out, if you will. There's going to be outputs of matter. In the human body, we have various outputs, whether it's energy that we're giving off, sound energy, some heat energy that I give off, waste products, whether it's sweat, urine, etc. Forest is going to have outputs. The the water comes in and it flows out. The tree grows, it dies, comes down. Certain matter goes out of the forest. Energy and information. And all of these systems wind up having feedback loops, some way to kind of know what's going on. We talk about these feedbacks because feedback affects behavior. Think about you as a human. Depending on some sort of stimulus that occurs, your body gets feedback. I put my hand down on the table and it's hot. I pull my hand away. There's a feedback. There's a loop involved to make me react to the situation. And all systems have feedback loops that are either built in or part of their natural evolutionary nature, if you will. So once again, we talk about they all have these inputs, the throughputs, outputs, etc. What is there? Well, let's touch base on these feedbacks. It's any process that increases or decreases a change in the system. Largely, we're going to talk about two. It's either going to be a positive feedback loop or a negative feedback loop. Now, unfortunately, these are kind of different from the end result, what we think of. So let's start with a positive feedback loop. That is any kind of a feedback loop that causes the system to change in the same direction. Early in Chapter 2, the case study was about the Humboldt Forest. In the forest, the scientists dammed up a stream in one, dammed up a stream in another area. Then they took the forest and they cut it down near one, left the other the same. When they cut the forest down, they created a positive feedback loop. Erosion is just kind of part of nature, but when they took out the vegetation, as the erosion started, it caused more soil to wash away, caused more nutrients to leach out, meaning less things could grow there, and the pattern of erosion grew and grew and grew. Positive feedback loop. As everything came into the system, the situation kept growing more and more and more. So it was a positive feedback loop. Caused the system to change in the same direction. So it's a positive feedback loop because as whatever is happening to the system, the same thing keeps increasing. As a general rule though, positive feedback loops are bad. They're not good. They tend to exasperate problems like the deforestation. As the forest was cut down, more soil eroded, less things could grow, more nutrients washed out, less things could grow, so the forest kept getting thinner and thinner and thinner. So it was a positive feedback loop. The effect kept getting bigger, but it tended to have a negative side effect. So that's a positive feedback loop. Whatever is going into it causes it to get more and more. This would be like if I go outside in the sun causes me to get warm, and my body gets warm, and I keep getting warmer and warmer and warmer. What would happen? Eventually, heat stroke, and I would die. Positive feedback loops tend to have a negative outcome. Now, negative feedback loops, also known as corrective feedback loops. They tend to cause the system to go in the opposite direction. Let's take this one with my body that I just used. I go outside in the sunshine, and so I wind up getting a little hot. What does my body do? It produces sweat. What does the sweat do? Causes my body to cool off. So it's a negative feedback loop. I go out, I begin to get warm, my body begins to sweat, therefore causing my body, the evaporation process causes a cooling effect on my skin, causing my body to cool back down. Negative feedback loop. It causes systems to change in the opposite direction. A house and a thermostat are a great example. Now here in Florida, the book talks about how the furnace would turn on and off. We're not going to use the furnace, we're going to use air conditioning. Because I wake up in the morning, the house feels nice. Mid-morning, the sun's hitting on my house, it's starting to get warm. As a house warms up, the thermostat kicks on to turn the air conditioner on to cool the house back down. The house gets cool enough, the thermostat kicks off, then it warms back up, the thermostat kicks back on, turning the air conditioner on, the house cools back down. This is a negative feedback loop. It keeps the house at the same temperature. If it was a positive feedback loop, it would be like the house caused the thermostat to turn on or turn off, and the house get warmer and warmer and warmer. Negative feedback loops tend to have a good outcome. Positive feedback loops tend to have a bad outcome. Negative feedback loops tend to have good outcomes. What we're actually after. Most systems in nature actually use negative feedback loops to enhance their long-term stability. In nature, it happens all the time. If a tree dies, the sunlight comes in, another tree comes in and grows into that space, providing shade yet again, keeping the forest at more of a even keel, and it regulates temperature in the forest and also other areas. However, we can get to tipping points. An ecological tipping point is when a system is stuck in some kind of positive feedback loop. I'm going to go back and talk about the ozone layer. We were using chlorofluorocarbons in a lot of things we did. The chlorofluorocarbons went up into the air and they began causing the ozone to break apart. More fluorocarbons went in, more ozone broke apart, there wasn't much there, and it was this positive feedback loop. Kept causing the ozone to get thinner and thinner and thinner. But when we stopped using the fluorocarbons, then it went back into a normal check and balance, and the ozone is repairing. But we can get to these tipping points. We reached a tipping point, it's correcting itself, but it's going to take a long time to heal. We think by 2050, then the ozone should be completely healed. But we had reached a tipping point that had probably gotten so big that we stopped what was going on, but it's taking a long time to correct itself. So in environmental science, these are the things we look at, these tipping points. Where are they? At what point have we crossed a line that something becomes inevitable? It's not that it can't heal, but once again, maybe not in a human time scale, especially not like your and I lifespans. So they can change so drastically that it'll suffer from severe degradation. The warming of the oceans. As the oceans warm up, as we get climate change, as global warming affects the oceans get warmer and warmer, carries that warm energy up to more and more land masses, and it's a positive feedback loop. It keeps getting warmer and warmer and warmer. We don't have some of the natural things to take it back. So we have to look at where's the tipping point? At what point does something become inevitable? Just like you leaning back on your chair in school. I've seen it 100 times. Makes me laugh every time. You're leaning back and I may say something like, hey, all four on the floor. And then all of a sudden you lean a little too far and whoop, you're on your back. It's a tipping point. At a certain point that you will fall over. It's inevitable. And this is what we're looking at. Where is that tipping point? It can happen, but we can still correct it. It can still be corrected. But at a certain point, they're not as correctable. Or, once again, it takes longer than a human time span for it to correct itself. So, just like in the Humboldt Forest, the loss of trees and the vegetation altered that forest's ability to retain, recycle water, recycle the nutrients, and etc. And a lot of its biodiversity goes down. It's biodiversity. Some animals can't be there, some plants can't be there, then they're not producing the things in the forest, and it gets problems and problems greater and greater. The plants and the soil nutrients simply get lost. So in environmental science, we want to look at these positive feedback loops and do they need to be corrected? And very specifically, we want to look at these positive feedback loops and look for the tipping points. Because once we reach a tipping point, now once again, these things can be in years. We think we're getting to the tipping point. There's a complex system. It can be hard to know exactly where it's going to be and what the corrective behavior may need to happen. With the ozone, we stopped using the chlorofluorocarbons so the ozone could heal itself. Problem is, chlorofluorocarbons last in the atmosphere for 50, 60 years depleting. So, tipping point. What we're looking for and how to correct it. Well, take care, guys. That is it for Chapter 2. See you next time when we look at